So let me start with a little thought experiment. Imagine you flip a coin, say, 100 times. You
Okay.
expect 50 heads, right? But what are the odds you get something really different, like 70 heads? I mean, how do we even measure that gap between our expectation and, well, reality?
And that
Yeah.
gap is precisely what we're here to talk about.
Yeah.
It's really the core mission of this deep dive into Hoeffding's inequality.
Hoeffding's, okay.
Yeah, it was proven back in 1963, and it gives us this really robust mathematical ceiling. It's what's called an upper bound.
An upper bound on the probability that our results are going to stray too far from what we predicted.
Exactly. And the key here, the really important part, is that it applies to what we call bounded variables.
Bounded variables. So for anyone listening, what does that actually mean? Why is the bounded part so important?
Well, it just means the outcome has to fall between a set minimum and a maximum. Think about your coin flip. It's either heads or tails, 0 or 1.
Or a poll result, which has to be between 0 and 100%.
Perfect example. And what's fascinating here is that if you sum up a bunch of these independent bounded events, Hoeffding's guarantees that your total sum stays really, really tightly clustered around its expected average.
But hold on, aren't there other tools for this? I mean, I'm thinking of things like Chebyshev's inequality or maybe the central limit theorem. Why do we need Hoeffding specifically?
That's a great question, and it gets to the heart of why it's so powerful. Those other methods give you good bounds, for sure. But Hoeffding's gives you an exponential bound.
Exponential.
Right. So instead of the chance of error shrinking, polynomially as you add more data, it just collapses. It falls off a cliff exponentially. The number of samples, what mathematicians call n, it just crushes the uncertainty way faster than you'd think.
That sounds incredibly useful. I mean, we're moving straight from theory into something you can actually apply, like with confidence intervals.
Absolutely. The number one practical use is probably planning your sample size. Hoeffding's can tell you exactly how many samples you need to collect to be, say, 95% confident that the average you're seeing is close to the true average.
So it's not just a theoretical line in the sand. It's a recipe. It's telling you how much data you need to gather.
It is. And the sources pointed out this amazing little insight about precision.
Oh, right. The efficiency game.
Exactly. When you look at the formula for sample size, the precision you want, let's call it epsilon. That term is squared.
What does that mean in practice?
It means the cost of getting more precise is quadratic. So if you want to double your precision, you don't just need twice the data.
You need 4 times the data.
You need 4 times the samples. It's a huge insight for anyone designing an experiment.
And that kind of efficiency in quantifying certainty, I mean, that's just critical for building reliable systems, which, feels like a perfect moment to mention our sponsor. This deep dive is brought to you by Embersilk. If you need help figuring out where AI agents could make the biggest impact for your business, check out embersilk.com. They cover everything from AI training and automation to software development. They really help turn this kind of mathematical certainty into real-world solutions.
And that's a great tie-in, because if we connect this to the bigger picture, Hoeffding's inequality is really the mathematical bedrock for so much of modern technology.
You mean like in machine learning?
Especially in machine learning.
Yeah.
It's the guarantee that your model, which is trained on a small, bounded sample of data, will actually work reliably on all the unseen data out there in the world.
So this math from the 60s is what gives us the trust we need for today's autonomous systems to actually work.
Yes, precisely. The ability to manage and to put a hard number on uncertainty, to know the exact cost of a certain level of confidence, that's a cornerstone of modern progress. It ensures our complex systems are built on a foundation that's quantifiably trustworthy.
That's a really inspiring way to think about it. That even in a world that feels so random, we have these focused mathematical principles that let us manage that randomness. And that opens the door for, well, predictable and incredible innovation.
It gives us the confidence to keep building.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.